Okay, so in this next series of videos, we're going to be taking a look at the general motion of a particle in 3D. We're going to start by generalizing from what we've done so far in 1D to go into 2 and 3D, and then we'll take a look at a few additional examples near the end of the video series and do a little more with constraints. But for now, we're going to start by taking a look at the general principles of 3D motion. Oops. So we'll start with Newton's second law. We'll go with the way that Sir Isaac actually wrote it, which is F equals dp dt. And if we follow what that means, remember, think of this as a collection of three equations that we're writing all at once. We write it once for the x component, then again for the y component, and then again for the z component. Now, this is the correct way to express it. And we've already seen that there are some cases where we actually do have to worry about writing it as momentum, namely if the mass of the system is changing with time. So for instance, if we launch a rocket or we make a raindrop fall, something like that. Since that's such a small percentage of what we're usually interested in, I'm going to leave that go off to the side. And also, this expression is the one that we use when we use relativistic momentum, but this is classical mechanics, and so we're not going to concern ourselves with the relativistic expression. So, in that case, where m dot equals 0 and we're classical, that trio of relations becomes fx equals mx double dot, fy equals my double dot, and fz equals mz double dot. Now, about the most general form that we could imagine writing a force. We could imagine writing our force as a function of position, velocity, and possibly an explicit time dependence. Although, generally speaking, you don't really need to sweat this one too much. As we will encounter much later in the course. Theorem due to M.E. Nether basically says that if a force depends explicitly on the time, then energy conservation is broken, and that gets to be a pretty hairy regime to analyze. Nether's theorem says a lot more than that, but that's definitely one part of it. However, position and velocity we can certainly imagine. For instance, gravity very definitely depends on position. So does the electric force. And the magnetic force depends on velocity. So we can have both of these being possible. All right, so let's remember how we found kinetic energy. So we're going to go towards developing a 3D generalization of work. Now, when I took vector calculus, generally speaking, what turns out to often be the case is things that are true in 1D are true in many of them are true in higher dimensions, but the proof for 1D and for any other dimension is totally different. So usual rule of thumb is if you can construct something in 2D, it isn't too hard to bootstrap it up into 3D or whatever you need. And that's going to be the game I'm going to be playing for the most part here, is a lot of this I'll just do in 2D, and then I'll say, trust me, it isn't that big of a stretch to bootstrap it up to 3D. So let's go ahead and remember how we found our kinetic energy. So the power is equal to F dot V, so that would be dP dt dotted with V. But that would be d dt of mv, which will dot with V. We can pull the m out of the derivative if we want. So we'll have m times v dot times v. Now, sorry, dotted with v. Now, if we're clever about this, we can recognize that if we were to then add to that m times v dotted with v dot and then divide by 2, we can wind up writing this as d dt of 1/2 mv squared. So the result that we get out of this is that our f dot t is equal to dt dt, or the power as I advertised before. So if we follow that thought a little further, v is dr dt, so this is f dotted with r dot is equal to t dot. Okay, now if we follow that, so, or f dotted with dr dt is equal to dt dt. And so then if we look at just some infinitesimal, we get that f dotted with dr is equal to dt. Now, so far, this is just, we've been working in 1D, but since we're going in infinitesimals, whatever path that we might conceivably care about, we could imagine getting our infinitesimals small enough that they are just line segments, and so we can actually bootstrap our 1D up into 2D, 3D, whatever we need. So we get our change in kinetic energy by integrating, and this is a line integral, or a path integral. F dotted with dr will equal the change in the kinetic energy of the system. Okay. Now our goal is just like before. We would like to be able to extend our idea of potential energy to higher dimensions than just one, and we play the same game as before. If our force is conservative, so if F is conservative, we should be able to write our path integral, f dot dr, be equal to some negative delta v, which will be the negative of where I ended up at, vb minus va, or if I prefer, I could write that as va minus vb. Now, the deal is here, this bit here depends on the path, and this bit here only depends on the endpoint, so it doesn't depend on the path. Now in 1D, that's less of a problem because there's only one path you could possibly have. But in higher dimensions, we can imagine a infinite number of possible paths that connect our two endpoints, A and B. So for us to tell if a force is conservative, we're going to probably the easiest thing for us to do is to go and take a look at closed paths. In that case, for a closed path, the change in the potential energy would be 0. So we can go ahead and map our force field by measuring the acceleration, say some small test masses, so objects so small that they're not likely to go and mess anything up. So for instance, we could go and take a look at a force field like, whoa, where did it go? Oh, that's awesome. Let's try that again. Can go take a look at a force field like this one, hopefully. There we go, ish. So we'll need to move that a bunch. Resizing probably good too. There we go. So here what we did was we just had a bunch of small test masses, and a test mass is just some mass that's so small that it couldn't mess up whatever it is that's generating the forces here. And we just plot the acceleration everywhere, and then from that we can deduce if I were to put an object, say, here, it would feel a force proportional to the length of the arrow. So this is one possible force field that we're looking to see if it's conservative. Pro tip, this particular one isn't. And the reason why the closed paths isn't such a bad deal is we can say, look, go from A to B and then return from B to A. If it's conservative, the change of potential energy here and there should be negative, so it would add up to 0. So if we demand that this is working for every possible closed path, it'll include those closed paths that connect A and B, and more to the point then will tell us that the potential energy is conservative. Okay, now that looks and sounds absolutely horrifying, but I promise you it isn't as bad as you might think. Because part of the trick we can do, and I promise this generalizes to 3D, but I'm only going to do it in 2D, is what we can imagine doing is subdividing, say, this horrendous little peanut here. Into, doggone it, into some boxes like so. We'll do another box like so. Oops. Now it won't. All right. So now if I look, say, like right in this bit here, I'm going to integrate both of these counterclockwise. But we can see that where the boxes overlap, I'll have a piece going this way to the right, a matching piece going to the left there. And that bit right there cancels. So you can imagine the program here. I can make any path I want by just nesting in an arbitrary number of nested rectangles um, until I get the border of all of the nested rectangles to match the path I actually care about. And then all these internal bits here will just cancel out. And so I can do it just for the rectangles and be happy. Um, In fact, I can even go ahead and subdivide the rectangles down into squares. So all I really have to worry about and to see if my force is going to be conservative is to go and take a look and say, well, will the path integral f dot dr equals 0 for a small square at any location? That really isn't as bad as it looks. It's definitely a lot better than where we were before. We've got it down from every possible arbitrary shape to any curve down to squares. And so now all we got to do is think really hard about the squares. So let's do that. Let's think about some candidate point here, xy. So my path that I'll take, go off to the right like that. So our next step here is we're going to end up at x plus delta x comma y, and then we'll go up and end up at x plus delta x comma y plus delta y, head back to the left. So we're closing off our square. That will be located at x comma y plus delta y. And then finally, I return back home. Okay, so that's the path that I have to worry about. So for my integral, integral f dot dr, I break this into 4 integrals. The first of them is going to be an integral from x to x plus dx, f sub x at y dx. So I'm looking at just the x component of the force, and I'm integrating it at some specific y, for some constant y value as I go from x to x plus dx. So that's the first leg there. So I've taken the dot product because here my displacement is purely in the plus dx direction, so f dot dx just becomes that much. All right, then the next step here, my displacement will be purely in the plus dy direction. So this will be integral from y to y plus, I'm sorry, not dy, not dx rather, but delta x, and this will be delta y. So again, here this will be f sub y evaluated at x plus delta x dy. All right. Now, for the next 2 legs here, and I'm going to write them a little weirder than makes sense, but I promise you it will make some sense. Now, in this next leg here, I'm going to get something that's going to look like an fx at y plus delta y dx. Now, normally you would be saying, well, okay, so that I'm heading in the minus dx direction, so I should really have a minus sign in front, but I'll be integrating from x plus delta x just to x. So if I flip the order of integration, I can keep the plus sign. If I flip the order of integration, it'll be consistent with this order of integration, which will make things easier in a second. Okay, and then similarly, we'll have a from y to y plus dy fy of x dy, like that. And again, same deal. The direction of integration is in the minus y direction, so I should have a minus sign, but I'm reversing the order of the integration to make the minus sign go away. So if I do that, so now I'm going to add these terms here like it sort of suggests. So adding the first term, I'm going to have an integral x plus delta x of, now here I'll have fx of y minus fx of y plus delta y dx. My bad there, I actually had 3 minus signs going, so this, yeah, I actually had 3 minus signs going here. When I flip the order of integration, those should be minuses there. My bad. There, much better. And then similarly from here, I will have plus y to y plus delta y of fy at x plus delta x minus fy at x dy. All right. Now, we're imagining that this is going to be a small box. So since this is a small box, I can go ahead and Taylor expand this f of x of y plus delta y about y. And similarly for f of y. So my f sub x at y plus delta y would be equal to f sub x at y plus the partial derivative of f sub x with respect to y, delta y, plus higher order terms. And what we're going to do is we're going to pinky swear that the box is small enough that the higher order terms don't matter. Similarly, we can say f of y at x plus delta x equals f sub y at x plus partial f sub y partial x delta x plus, again, higher order terms that we're going to, again, make the box small enough so as to not matter. So now what that means is for my integral f dot dr about my small box, this will become an integral from x to x plus delta x. Well, now when I substitute this in, I'm going to get some fx's at y that cancel, and I'm just left with this partial derivative here. So I'll have a minus partial fx partial y delta y dx plus integral y to y plus delta y. And then same deal here, except here it's going into the first term, so we're left with the positive sign partial fy partial x delta x dy. Okay. So now when we go ahead and evaluate this, it's over a small enough interval that this partial derivative, remember we're valuing this partial derivative at a point. So the integral over dx is just going to turn into a delta x, and the integral over dy is just going to turn into a dy. So I get minus partial fx partial y delta x plus partial fy partial x delta y. Well, in both cases, I look at these and go, hey, that's the area of our box. So we can group that out and finally get a partial fy partial x minus partial fx partial y times our area. Okay, well the area doesn't matter so much. The area will be non-zero, and if we're testing for force being conservative, the thing in front of the area is the thing that had better vanish. But yeah, if we squint an awful lot at this, this kind of sort of looks cross-product-y, doesn't it? You know, we've got an x, y minus a y, x, kinda. So what we're going to do is we're going to go ahead and define the del operator. Some math professors will call this nabla. Pretty much every physicist I've ever known calls it del, as do most mathematicians. So anyway, del is defined to be I hat partial x plus j hat partial y plus k hat partial z. So now the way to think about an operator here is if I go ahead and say left multiply it, if you will, against something. So I, say have del times a, for instance. What I would be doing is taking the partial derivative of a with respect to x, multiplying that by I hat, y with respect to x multiplied by j hat, z with respect to x multiplied by k hat. That will give me some sort of vector in this particular case. In fact, that vector would be what we call the gradient. So this is also known as the gradient operator. That's all well and good, but for our result, we look at this and we recognize that what we've taken here is the z component of the cross product of this del operator with f. So I did that in 2D, but our 3D generalization of this, so the general case is going to be that our integral of f dot dr is going to equal so this integral with an s here, so this is going to be an integral of our surface that's bounded by some path of del cross f dotted with n hat dA. Okay, now there's a lot of pieces to that, and let me give a lot of these have names. This del cross f gets called the curl of f. This n here is the unit normal to the surface. The dA is a differential area that our unit normal is currently attached to. The whole thing is actually a result from vector calculus that gets called Stokes' theorem. And I have to say, it is very clever. Now, again, just a quick reminder here. Since we can pretend like the curl is a cross product, we can go ahead and remember it by the same mnemonic we use for cross products. So I, J, K, like that. We're going to pretend to take a determinant of a matrix, even though at this point the meaning of a matrix that's filled with vectors and operators is incredibly suspect, but it's just a mnemonic to help remember what we're doing. Partial z, fx, fy, fz, like so. And then you can go ahead and plow the field or expand minors or whatever method you like. So for instance, if I go ahead and plow the field here, we'll be doing this minus that. So that will be partial f partial y minus, try to say partial f sub z partial y minus partial f sub y partial z. That'll be the x component. And then similarly for y and z. Okay, so how do I go about interpreting this curl? Well, other names that you'll find for, or at least other symbols that you'll find for it, you'll find some older texts that will call the curl the circulation. And you'll find certain texts, especially in German, rather than writing curl, will write R-O-T. So in a certain sense, what it's doing is it's telling us how a vector field is, say, quote, rotating or, quote, circulating. The picture that I always imagined was if we imagine sticking a paddle wheel in, it would tell us which way the paddle wheel would spin. So if we go back to this guy here, let's go ahead and imagine that we stick in a paddle wheel right here. Well, we imagine that the vector field here is water going by, and the length of the arrow tells us how fast the water is going. Well, then if we look at this side of the paddle wheel, it's going to get hit harder than this side of the paddle wheel. And so the whole paddle wheel there is going to want to rotate counterclockwise. So what this tells us is that we have a non-zero curl. So this particular force field would be not conservative. But that's what I usually do, is if I see a little map like this, I just imagine plunking a paddle wheel in there and imagining which way it spins. Okay, so we can go ahead and do an example of this, say just with circulating water flow, just to get a quick feel for an example of that. So let's say the position of our water is r times I cosine omega t plus j sine omega t. Then the velocity would be r dot, so that's, let's see, we're going to pull out omegas from each of these when we differentiate. Our omega derivative cosine is minus the sine, so this will be minus I hat sine omega t plus j hat cosine omega t. So then if I wanted to, I could go ahead and take the curl of this. Pardon me a second here. Before I do that, let's multiply this r times the sine and the cosine. Oh wait, that's y and x. So I can rewrite this as omega times minus I hat y plus j hat x. Now let's go ahead and take the curl. So the curl v there is going to be equal to, well, I can pull the omega out, it's a constant. So then we go I, j, k, partial x, partial y, partial z, negative y, x, 0. So the we're only going to have two non-zero terms. So let's go ahead and plow the field and see it. So for I, we plow the field, partial of y of 0 is 0, and partial of z of x is 0. For j, partial z of negative y is 0, partial x of 0 is 0. For k, partial x of x is 1. And partial y of negative y is negative 1, but we're going backwards, so we subtract. So 1 minus a minus 1 is indeed 2. And so we get 2 omega k hat. So if we were to plot this, so here's my x, y, z like so. My water is circulating around like that. Whoops. It's circulating around like that. And my curl is pointing like that. So it matches the sense of the right-hand rule. If you put the thumb of your right hand in the direction of the curl of V, your fingers curl in the sense of the rotation of the fluid. So this 2 omega gives us the rate of circulation, and we also get the direction of the circulation. All of that from the curl. Okay, in the next video we'll take a look at the potential energy some more and look at a few examples.